Neutron stars are the densest objects in the universe that we can actually observe, and the numbers behind that density are far stranger than any description gives them credit for. Most explanations stop at incredibly dense, or a teaspoon weighs as much as a mountain. That is where things usually end. But the real story is in the math, in what those numbers actually mean when you follow them to their logical conclusions. Let's start with what a neutron star is, not in vague terms, but in precise ones. When a massive star, somewhere between 10 and 25 or more solar masses, exhausts its nuclear fuel, gravity wins. The outer layers explode outward in a Type II supernova. The core, however, collapses inward in less than a second. What remains is an object roughly 10 to 11 kilometers in radius, carrying about 1.4 times the mass of our entire Sun. To put that in perspective, the Sun has a radius of around 696,000 kilometers. A neutron star fits the same mass into a sphere about the size of a mid-sized city. Now here is where the math starts to get genuinely strange. The density of a neutron star runs from approximately 3.7 times 10 to the 17th kilograms per cubic meter up to 6 times 10 to the 17th. Those exponents are doing a lot of work. For comparison, water is 1,000 kilograms per cubic meter. Lead is about 11,000. White dwarf stars, already considered extreme, come in around 1 billion kilograms per cubic meter. A neutron star is roughly 100 million times denser than a white dwarf. That gap does not shrink when you stare at it. It gets more unsettling. The teaspoon comparison you may have heard is real, and it is worth doing properly. 1 teaspoon, 5 milliliters of neutron star material would carry a mass of approximately 5.5 trillion kilograms. The Great Pyramid of Giza masses about 6 billion kilograms, so that single teaspoon outweighs roughly 900 Great Pyramids, not the pyramids as a collection, each one multiplied by 900. But here is the comparison that lands harder for scale. Take the entire mass of Earth, every ocean, every continent, the entire iron core. At neutron star density, all of it compressed would fit inside a sphere 305 meters in diameter. That is roughly the size of the original Arecibo radio telescope dish. The whole Earth packed into something a person could walk across in a few minutes. So how does matter even reach this state? In a normal atom, the nucleus is extraordinarily small relative to the overall structure. If an atom were the size of a football stadium, the nucleus would be a marble at the center. All of the space in between is electron cloud. Neutron star formation essentially eliminates that space. The gravitational pressure during core collapse is so immense that electrons are driven into protons, forming neutrons, and the resulting neutrons are packed together at nuclear density, the same density found inside an atomic nucleus itself. The entire star becomes, in a real sense, one enormous nucleus. This is not a metaphor, it is a structural description. The density at the surface of a neutron star already exceeds 6 times 10 to the 14th grams per cubic centimeter. Deeper in, within about 4 kilometers of the center, densities climb past that. At the very core, they may exceed 4 times 10 to the 15th grams per cubic centimeter, a regime where physicists are not entirely certain what form matter takes. Exotic states involving free quarks or other particle configurations have been proposed. The interior of a neutron star remains one of the few places in the universe where the known laws of physics have not been fully tested. Now consider what this density does to gravity at the surface. The gravitational field at a neutron star's surface is approximately 2 times 10 to the 12th meters per second squared. Earth's surface gravity is 9.8. A neutron star's surface gravity is about 200 billion times stronger. If you dropped an object from 1 meter above the surface, it would hit at roughly 2 billion meters per second. The escape velocity from that surface sits at around 150,000 kilometers per second, approximately half the speed of light. These are not rounding errors or approximations. General relativity becomes a practical engineering concern at this scale, not an abstraction, which brings up something that tends to get overlooked in neutron star discussions. Time itself behaves differently there. Due to gravitational time dilation, a clock on the surface of a neutron star runs measurably slower than one far away. The difference is significant enough that for every 10 years passing on Earth, only about 8 years would pass on the neutron star's surface. Time dilation is usually discussed in the context of black holes, but neutron stars are close enough to that regime that the effect is real and calculable. When Jocelyn Bell Burnell discovered the first pulsar in November 1967, PSR B1919+21, the signal was so regular, pulsing every 1.3373 seconds, that the initial reaction from researchers was genuine uncertainty about whether it could be natural. It was catalogued informally as LGM1, Little Green Men. The precision was almost too perfect for an astrophysical source. What made that precision possible was the combination of extreme density and conservation of angular momentum. When the original stellar core collapsed, it spun faster, for the same reason a figure skater accelerates when pulling in their arms. A neutron star can complete full rotations in as little as 1.4 milliseconds, hundreds of times per second. The Crab pulsar, remnant of a supernova observed in 1054, still rotates about 30 times per second today and is slowing down at a measurable rate. This rotational stability, combined with the density, creates a clock-like regularity that has made pulsars genuinely useful as navigation and timing references. The millisecond pulsar, PSR J0737-3039A, with a measured mass of 2.6 times 10 to the 30th kilograms and a radius of 13.75 kilometers, is part of a binary system where both objects are neutron stars. These systems allow physicists to test general relativity in conditions unreachable by any laboratory. The Chandra X-ray Observatory, launched in 1999, has resolved neutron star structures through X-ray imaging at a level of clarity not previously achievable. Neutron stars emit primarily in X-rays, which means ground-based optical telescopes are nearly useless for studying them directly. Chandra has produced data tight enough to constrain equations of state for matter at nuclear density, feeding directly into the open questions about what the core actually contains. So what does it mean to hold all of this together? A neutron star is not simply a compressed version of something familiar. It is a category of object where the laws governing atomic structure have been overridden by gravity, where quantum mechanics, nuclear physics, and general relativity all operate simultaneously, and where removing any one of those frameworks leaves the description incomplete. The density is not just a large number, it is a signal that something qualitatively different is happening at every scale. From the behavior of individual particles to the passage of time. The math does not make neutron stars easier to imagine. What it does is make the failure of imagination precise. And that precision is more honest than any analogy. If you enjoyed this video, consider subscribing to the channel.